Good evening. This is our project presentation of physics prepared by Group 5, which is consists of En Jun Heng, Eugene Lee Chi-kyung, Ho Jian-xian, William Qing Zhen-ye, and me, Yap Xing-chin. Our project will be investigating the relationship between quiet turns and launching force in a solenoid-based quiet gun. It's an experimental study of electromagnetic principle. This will be our table of content, which consists of introduction and background, objective, project scopes, methodology overview, key finding, data observation, analysis, and conclusion and future recommendations. That's all for me. Thanks.
Let's start with an introduction to solenoids. A solenoid is a coil of wire that creates a magnetic field when electricity flows through it. It's very useful in machine and automation because it can generate magnetic force without physical contact. One existing application of solenoids is in projectile launchers, where they use electromagnetic pulses to push objects forward. This technology is used in the military, space research, and even in education. Now, let's talk about the purpose of this study. We want to find out how the number of coils turns in a solenoid affects the launching force of a coin gun. By understanding this, we can improve the performance of this system and make them work better for different uses. Let's talk about the scope of our project. First, we set up an experiment where we change the number of coins turns in the solenoid. Next, we measure how far the projectile traveled and how fast it was launched. Finally, we analyze the data to look for patterns and understand how the coin turns affect the performance.
Okay, as for methodology, we have the materials, magnet, enamel, copper wire, solder can, pull tab, paper cup, DC power supply, cable tie, and straw. As for our procedure, we wind the coils with different turn counts on the straw, and we connect the coil to the power supply, and we measure the effect of varying turns on projectile launch. As for our measurement tool, we use ruler and string. After this, we will be showing a demonstration of how we do our experiment in detail, I think.
For our products, we are using a solenoid-based electromagnet. So we make our solenoid electromagnet using a copper wire and then wounded around the straw core. So the straw core, there is a hollow inside, which enables us to put our projectile into it. And then for our launching base, we are using a paper cups. We utilize the solder can pull tabs and then install on the above sections. There's a hollows in the pull tabs. Later we can install our straw core wire into it. So we kind of hold it in the place and hold it stably and then make sure it hold firmly. And then for the power supply of our project, we are using just a laptop cable. So this is a negative terminal and this is the positive terminal. So I'm going to connect the one end of the copper wire to the negative terminal. So due to low budget cost, I'm just using a drying pads, no crocodile clips. To connect the circuit and let the current flow in the circuit and generate magnetic fields, you just touch it and actually you generate magnetic field. To show there's magnetic field produced inside the solenoid when there's currents, I'm going to use this, the screwdriver. I'm going to just put in this place. If there's magnetic field, you will see that this screwdriver will be pulled inside into the wire. So now I'm going to complete the circuit and later you will see. So you see this screwdriver in this pulled into the straw. So this means there is really magnetic field inside the solenoid. So now this is our projectile. So this projectile consists of 4 button magnets attached to each other to form a cylinder shape. So this will be our projectile. We're going to insert this into the straw, and then I just put it near to the solenoid ends but not into it. So now I'm going to complete the circuit just very quickly and then disconnect it. So I do this by just touching the 2 wires very quickly and disconnect them. So you see the magnet is launches out, and we are going to measure the distance between this starting point to the landing point. We measure the distance between it and then we collect the data.
In our key findings, we observe 2 important points. First, there is a direct relationship between the number of coil turns and the launching force. As the number of turns increases, we identified non-linear effects caused by limitations in the launching mechanism. In the current slide about data and observation, we analyze the relationship between the number of coil turns and projectile performance. The table summarizes key data. As the number of coil turns increases from 50 to 200, both the projectile range and velocity show insignificant improvements.
In the previous sections, we have gone through the data, and in these sections, we are going to take a closer look on what this number really means. We will analyze the key trends derived from our data, helping us to understand the implications and how they tie back to our objective. First, we observe there is a linear trend between 50 to 100 tons and 150 to 200 tons. This linear behavior is aligned with the theoretical model of Ampere's circular law, which states that the magnetic flux density of the solenoid is directly proportional to the number of turns of coil, and additionally, the magnetic force acting on the projectile itself is also directly proportional to the magnetic flux density, according to Lorentz force. However, we also observe the non-linear increase between 100 and 150 tons, and this is due to the limitations of using a 2-wire manual contact mechanism that is used to triggering the circuit, and also the absence of current monitoring system in our circuit, which led to the inconsistency and also inaccuracies in our experiment result. In conclusions, more coil turns increase the magnetic flux density and also the projectile force. In order to achieve a more accurate data and experiment result in futures, a circuit auto-triggering mechanisms should be implemented to improve the consistency in the activation. And we need to also incorporate a current monitoring system to avoid variations in current that lead to inaccurate outcomes.